Okay, before we get to this picture, I want to explain a couple of terms. We're going to come back to these two terms in just a few minutes, but I have them here, so I'm going to explain some things. Muscle tension. Okay? This idea of muscle tension is just the force exerted by a muscle on an object. So we have muscle tension, right? We're building up tension. Now, when you think of muscle tension, the easiest thing to think about is, okay, well, we're moving the load. In this case, this is a stapler, right? So I have a muscle, which is the biceps brachii, and I'm moving the load, right? And in so doing, what happens to the muscle? Well, the muscle gets shorter. It's moving the load, the muscle gets shorter. We call that simply muscle tension. But in reality, if I try to lift up this desk, and I'm lifting and lifting and lifting, it's still muscle tension. I'm still building up muscle tension, but there's a difference. Okay? I'm not moving the load, and the muscle does not get shorter. It only gets shorter if you move the load. And so depending on how heavy the load is, and the load would be by hand, the weights of all the bones and muscles and skin and the stapler, depending on the weight of all that, if I can overcome the load, then we call that an isotonic contraction. Isotonic. And again, in an isotonic contraction, the muscle gets shorter and the load is moved. In an isometric, or same measure, if you want to go back to the root words, it just means that the muscle tension develops, but you don't overcome the load. So you don't shorten the muscle, the load does not move.
Can you say that again with the contraction, the isotonic?
So isotonic means that the load moves and the muscle shortens. Isometric means the load does not move and the muscle does not shorten. So same measure, isometric. We'll come back to these ideas a little bit later, but just wanted to introduce the idea of muscle tension, load, isometric, and isotonic contractions. Let's talk now about something called a motor unit. This is actually something that your book doesn't go into great detail about. It calls it something different, and I'll show you what that means in a couple of minutes. But I think a motor unit makes more sense, and so that's the way I might teach this. So imagine we have a muscle. Okay, let's just imagine it's a muscle in my hand that would just kind of slap this desk right here. Now, I could take this muscle and I could tap the desk, or I could take the same muscles and really hit the desk. Well, how? How can I control the force of the contraction? Well, there's a couple ways we can do that. We're going to talk about how that can happen. And this is one of those ways. We talk about motor units. We talked about a neuromuscular connection, or a junction, right here. So you can imagine that we have one neuron from our central nervous system, in this case it's coming from the spinal cord, one neuron that's going to attach to these two muscle fibers. And we're going to get another neuron that attaches to these muscle fibers. So if I want to weakly tap my cheek, I may only turn on motor unit 1. That's going to cause a few of the fibers, but not all the fibers, but only a few of the fibers in my muscles to contract, and it gives a weak force of the muscle. If I want to make the force of the muscle stronger, then I'm going to employ or recruit more muscle fibers. And this idea of recruitment, we're going to come back to again and again and again. It's kind of like this. A few muscle fibers can try to lift up this desk. This is a piano, okay? But what I'm going to do is I'm going to say, you know what, I can't lift this piano by myself. I'm going to call my friends. I'm going to recruit my buddies. And we're all going to come up here, and together we're going to lift up this piano. You're going to recruit more fibers until you get full recruitment. Once all the fibers in the muscles are recruited, that's as far as the muscle can go, right? But you can get a graded response. You can get different degrees of contraction by how many fibers you turn on. So we call that a motor unit. A motor unit is simply the neuron and its associated muscle fibers. Does that make sense? Motor unit. Let's talk about this. This is not the same thing we were drawing before. This is looking at a muscle contraction. Okay, so ignore the picture we talked about before class, before break. This is the force of a muscle. This is muscle tension on the y-axis. You get muscle tension. So imagine right here, let's picture this. I have a muscle. I've taken this muscle out of, let's say, a frog. Okay, for simplicity. And I have that muscle in the laboratory in a petri dish. Has anybody ever done this? Anybody ever taken a dead frog and hooked up a battery to it and watched it twitch? You guys never lived. Come on, you got to do that.
I've dissected a live frog.
Yeah, well, there you go. If you put electrical impulse into the muscles of the frog, they'll kick.
We didn't do that part.
Yeah, it's just never. All right, it's fine. So let's imagine right here we have a muscle cell. We have it in the lab, and all we're going to do is we're going to put an electrical probe right on the muscle cell. And we're going to hit a single charge, just zap a single charge right to it. That's the charge right there. We zap the muscle. On the x-axis here, we have time. So notice something. We zap the muscle here, and there's nothing that occurs for a short period of time. There's a short period of time where the muscle does not contract. Why? Well, we just talked about it before break. You get that electrical impulse that propagates down the sarcolemma, has to go down the T-tubules, then has to release calcium. Calcium has to go to troponin, tropomyosin, and then eventually lead to contraction. That takes time, and that's what's represented here by the latent period. Okay, there's a short period of time for that excitation coupling to cause contraction. Then you see this rapid contraction of the muscle. And that's what this is here, building up muscle tension. Then it reaches the apex, then you have a long relaxation period until it goes back to the resting state. That's a typical muscle twitch. A muscle twitch. We zap the muscle one time, we see an increase in muscle tension, and then a decrease in muscle tension. Muscle twitch. This is a laboratory phenomenon, but this is how we study muscles. This is how we understand how muscles work in a live person by studying individual muscles and how they respond to stimuli. Your question, Cody?
Okay, so the top of that, is that when all your muscles are contracting?
We're just looking at one muscle.
So this is just one.
One. So the best way to think about this, again, is it's a laboratory phenomenon. We're studying a single muscle in the laboratory in a petri dish. And we're going to extrapolate that knowledge of how muscles respond to how they respond in the whole body. Different muscles respond differently. This should not be a surprise. So think about the muscles that are in your eye. Rapid eye movement, right? We're talking about all over the room. You can turn your eyeballs really, really fast. Okay? Turn your eyeballs, look at different things. As opposed to the muscles here in the calf, the gastrocnemius and the soleus. Those two muscles are really more designed for stamina, for endurance. And so if you look at the speed of contraction, some muscles have very fast contractions and very fast relaxation periods, whereas other muscles are slower to contract and slower to relax. Yes, Mom?
Is that where we get into the fast twitch and slow twitch muscles?
Yes,
Kinda.
kind of. But we will get there, I promise. Right, this has everything to do with the muscle fibers inside the muscle. So let's look here, again, we're looking at a laboratory phenomenon, and you can imagine this is what they call a myogram. All that is, it's just showing you muscle tension on some sort of monitor on a computer screen. And you're looking here at muscle twitches. And so here are your stimuli. You give a single electrical impulse, and you see a nice single muscle twitch. The muscle contracts and then relaxes back to its original state. You hit it again. You hit it again. And again. And so you can imagine that muscle's contracting. Does that make sense? Now, this over here, I'll only explain real quickly. I'm not going to spend a lot of time on this. All this is really showing you is this Treppe effect. Okay? Now, I'll never ask you this in an exam. But I think it's good for exercise physiology. All I'm showing you here is that if you notice the amount of muscle tension, which is not shown here, but this is on the y-axis is muscle tension, builds up over time. The muscles are warming up. The more you work your muscles, the more muscle tension you're going to build in that muscle. And so there is truth to the fact that you go out and you exercise before you run a marathon, you'll run faster. I promise you. If you go out there cold, we've talked about this idea before, right? You go out there cold, your joints won't be warmed up, your muscles won't be warmed up. And there is true physiological reasons why you're going to run faster if you warm up. You know, it seems weird, but people who run a 5-mile marathon will run 400 or 500 meters before they run the marathon. You think, wow, they're wasting all that energy. No, they're not. They're getting ready to run full spread for the marathon. Okay? Okay, let's skip over that and go back to this over here. So what's happening here? Well, imagine as this is contracting and it's relaxing, what if instead of waiting all the way here to stimulus, to give the stimulus, what if I gave a stimulus right here? The muscle is not completely relaxed yet, but now I start here and I go up. And then I go up higher and higher and higher. So the faster I give the stimuli, the more and more muscle tension I build up, because I'm cutting into the relaxation phase. Does that make sense? You're building, you're building, you're building, until the stimuli is so constant, so rapid, that you get complete tetanus, or complete contraction. That's what we call tetanus. I know it sounds like the disease, and there's a reason for that, okay? If you have tetanus, you ever heard of tetanus? That's where all your muscles are contracting, and you can't stop. That's what having tetanus means. Okay? So that's where the name comes from. So complete tetanus is where the muscle is fully contracted. Now, we'll talk about this term again in just a few minutes. Fatigue. This is what we call muscle fatigue. This is not, oh my gosh, I'm so tired, I didn't sleep last night. This is not the physiological state of unrest. This is the physiological state in your muscle where your muscle physically cannot contract anymore. Even though it's constantly receiving stimuli, it is unable to contract anymore. It is fatigued, muscle fatigue. You should be aware of that idea. Okay? So what am I trying to show here? Well, imagine that this is one muscle fiber. Okay, we talked about this being one muscle. Imagine this is one muscle fiber, one muscle cell, right? So what I'm saying here is that this muscle fiber is going to contract, and the tension is going to build and build and build and build the faster the stimulus is. Right? Until it gets to a point where it's complete tetanus. If I just go like this, little charges, it'll be mildly contracted. And as I get more and more and more and more and more, it's going to build up more tension. So the frequency of stimuli increases the tension. Does that make sense? The frequency of stimuli. So that's one way to increase muscle tension. So you can go back to this picture. Let me go back right here. So imagine this muscle now, the entire context of the muscle. Motor unit 1 has a stimulus. Boom. But we can increase the muscle tension by increasing the frequency just on motor unit 1. Couldn't we? So we can increase the muscle tension, the overall muscle, by increasing the frequency of stimuli, but we can also increase it by recruitment, by getting more motor units involved. There's two ways to increase muscle tension: the frequency of the stimuli and recruitment. Does that make sense? That's a big picture. I put it all together in just a few minutes. Okay? We'll get there. It's actually, it says, if you look on page 18, it says summary of rated muscle response, right there in the middle. And I summarize that in a couple sentences. So that's what I'm building up to right here. So I'm going to show you how that works. Okay? Let's look at that. We have our muscle. Okay? We have our laboratory phenomenon where we're giving a small charge, right? We're shocking our muscle that's in the petri dish. What I want to point out here is a couple of ideas. Threshold. Threshold is a term you're going to see a lot in biology. Threshold means a minimum that results in an all or none kind of response. You're going to see what that means. So right here, we have a small voltage. Okay? Here's the voltage. Let's say we only hit it with a couple volts, right? And you see an increase in voltage, but it's not enough to reach threshold. So if you look here, the number of motor units excited is none. That muscle does not contract. It's not a strong enough voltage to reach threshold. You increase the voltage here. It's a higher voltage, but guess what? Still, no motor units employed. You still have no contraction of the muscle. You can see this down here. No contraction strength. So this is a nice picture. It shows you all the things going on. Here, third voltage. You reach stimulus. At this point, you turn on a couple of, in this case, muscle fibers. So right here, you see a small little increase in muscle tension. As you increase the voltage, not the frequency, but increase the strength of the voltage, right? You increase the strength of the voltage, you recruit more fibers. And that's shown here in muscle contraction. Increase it more, until a point where you reach the maximal contraction. It doesn't matter if you zap this with 1.21 gigavolts, whatever it is in that movie, right? It doesn't matter what you get it with. You are maximally getting all the motor units employed. Am I making that clear? So you increase the voltage and you increase recruitment. You increase the frequency and you increase the contraction, or the tension, muscle tension. And two things playing in one.
It sounds like a AM versus FM radio. If you're familiar with the amplitude versus frequency modulation.
Not really. I'm not. This is how your book shows the same phenomenon. Okay? Just to show you. They talk about it being nerve fibers excited. They don't use the term motor unit. So I like the term motor unit because it gets confusing to say nerve fibers excited. Like, well, what does that mean? Well, it's nerve fiber and associated muscle fibers. So it's called a motor unit. It's the whole thing. It's not just the nerve fibers. It's the nerve fibers and what individual fibers they're attached to. So that's why I don't like that. It's the same kind of thing. So here, muscle tension. We have a muscle. It's sitting in a laboratory. We hit it with a small voltage. And that voltage is enough to cause motor unit 1 to turn on. And that muscle will twitch. You'll get a contraction. But now we increase the voltage more. And now, in addition to motor unit 1, we also recruit motor unit 2. So now we've got 2 people trying to lift the piano instead of just 1. Increase the voltage even more, and now you have more people, more fibers trying to lift it up. And so through a course of action, by increasing the voltage, you're getting more and more muscle tension. Until eventually all the muscle fibers in that muscle are recruited. And that's as far as the muscle can go. Does that make sense? So as I said, the summary of rated muscle responses. I like that. I kind of wish I would have made it bigger when I made this up, but I didn't. So it says changing the frequency, the stimulation frequency, to a single motor unit, right, can produce a smooth, continuous muscle contraction by rapidly stimulating a specific number of muscle cells. In other words, it's about frequency, how fast the voltage occurs, the time between each stimulus, right? While increasing the number of motor units involved produces stronger muscle contractions by recruiting additional muscle cells. So that goes back to the increasing the voltage. So you have the size of the voltage, small versus large, and you have the frequency of the voltage versus rapid succession. And those two together will dictate the overall muscle tension. Being, again, weak or being strong. All right. Muscle tone, real quick, since we're on there on page 18. What is muscle tone? Well, we talked about it kind of quickly. If you think about muscles and you think about motor units, it makes sense how you can have muscle tone. If you remember, we talked about joints, and I said one of the reasons why joints are stable is because we have muscle tone, and that's that slow, I should say slow, that's the low level of contraction that every muscle has. Even if you're not actively using that muscle, there's still some muscle tension. Well, that muscle tension is done by motor units. So you can imagine that a motor unit will be working in your legs all the time. Okay? And after a couple of seconds, that motor unit will be turned off and another one will be turned on. And that'll be turned off, another one will be turned on. So they're just basically swapping back and forth to always give a low level of muscle tension in every muscle. And then that tendon that crosses the joint provides stability for the joint. So that's all muscle tension is, or muscle tone is. Okay? It's that constant, slightly contracted state of muscles that again provides stability, stabilizes joints. This is what helps posture. You stand up straight. Okay? Gives that ability is just basic muscle tone. So we talked about this very briefly. I'm going to tell you right now that the terms concentric and eccentric, I will not ask you on the page, bottom of page 18. I used to. But I think it gets people confused. And since there's enough today to worry about, we're not going to worry about that. So all I really want you to understand is the difference between isometric and isotonic. Okay? Isometric and isotonic. We talked about that before. This is another visual way of looking at it. Isometric means same measure. So this weight is too heavy. She's not able to lift it up. I wish they would have made the weight bigger, but they didn't. Okay? So she's not physically able to lift that up. The load is too heavy. The muscle does not shorten. The load does not move. Over here, she's able to lift it up. Okay? And in this case, she's got muscle shortening and the load is moving. That's all this talking about.
Would be like holding a plank position be an isometric?
Holding a what?
Holding a plank, push-up position. Only you're maintaining the line.
Possibly. Yeah. I know what you're talking about. Yeah. Muscle metabolism, starting on page 19. Has anybody had basic bio in this class? So you've studied glycolysis, Krebs cycle, oxidative phosphorylation. You guys will have a better understanding of this than anybody else in the class, and that's okay. I'm not expecting everybody in the class to understand the Krebs cycle, oxidative phosphorylation, or any of that stuff in detail. But I do want you to get a general understanding of where ATP comes from. So again, what is ATP? Well, it is what's needed to cox the heads of myosin, right? We need ATP. If you don't have ATP, the muscles will not contract. So if you're running a race and you're desperately trying to get to the finish line, or you're, let's say it's Halloween, right? You're running away from a monster or a ghost, right? You're trying to get away. You need a constant supply of energy. Constant supply. And we're going to get that energy in the form of ATP. Now, all muscles have a very small amount of ATP in them right now. A resting muscle has about 2 or 3 seconds worth of ATP. So it can contract, you can run for about 2 or 3 seconds. And then your muscles run out of ATP. And unless they can get more ATP, they're going to stop. But luckily we have another way of getting ATP. So in addition to the 2 or 3 seconds of ATP that's built up in your muscle, we also have something called CP, or creatine phosphate. Creatine phosphate. Yes, you should be familiar with this idea. Okay? Creatine phosphate is a high energy molecule, very similar to ATP. So I'm not going to get into details here with chemistry. They made it real simple. If you remember ATP, the reason why ATP is a high energy is because it has that phosphate bond, that extra one. And it's that high energy phosphate bond that gives it that energy. You break that bond, you release energy. You form that bond, and it needs energy. This goes back to chemistry. We talked about this once before. All CP is, creatine phosphate, is a molecule called creatinine that has a high energy phosphate bond on it. So all that happens is creatine phosphate breaks that bond, the phosphate group right off, and uses the energy of breaking that bond to reform ATP. So that phosphate just jumps onto ATP basically. And so you're able to regenerate a small amount of ATP. Enough for a few more seconds of running away from the monster. But that's about it. So you have some ATP built up, you have creatine phosphate, which is built up, then you use all that within 5 or 6 seconds of running. Now what are you going to do? Well, now you have to dump into one of these 2 pathways. And really both pathways start here. Okay? This is actually the first step in both pathways. So we're going to be talking about the anaerobic pathway and the aerobic pathway. Anaerobic means without oxygen. Anaerobic. Okay? That means it works in the absence of oxygen, or it works in the presence of oxygen, but it doesn't need it. It doesn't matter if there's oxygen there, it just doesn't need it. Okay? The aerobic pathway over here only works when oxygen is around. If there's no oxygen, or there's low oxygen, you cannot do it. It will not work. And if you've had basic bio before, you understand why. Okay? If not, don't worry about it. I'm not going to get into that kind of detail unless you want to know what's over break. Let's talk about this pathway first. So what's happening here? Well, sugar, glucose. What is glucose? If you remember, we talked about this idea. 1, 2, 3, 4, 5, 6. Okay? C6H12O6. Okay? That's glucose. What is that? Well, all it really is, it's 6 carbons. It's a 6-carbon molecule. Okay? What's going to happen is that's going to get broken down into 2 3-carbon molecules. We call these 3-carbon molecules pyruvate or pyruvic acid. Either one's fine. Pyruvate or pyruvic acid. Okay? I'll mark it on that.
So C3H6O3?
Yeah, C6H12O6. I wouldn't ask the detail, but if you want to know. So what happens when you take a large molecule and you break a bond and form 2 smaller molecules? May you remember? What happens when you break a bond? You release energy. You got it. So that energy that's being released, we're now going to use to drive this process. We're going to use the energy from breaking that bond of glucose down to pyruvic acid and use the energy to recharge our batteries to make more ATP. And basically what's going to happen is for every molecule of glucose, every 1 molecule, we're going to build up 2 ATPs. You don't need to know that number. Okay? If you were in another class, I would ask you to know it, like 101, biology 101, but not for here. Okay? So you're going to build up some ATP. So as long as you have a constant supply of glucose, you can build ATP. This occurs in the anaerobic pathway, meaning you don't need oxygen. If oxygen's there, you're fine. If oxygen's not there, you're fine. You can still make ATP as long as you have a constant supply of glucose. So you have glycogen. Remember we talked about glycogen as a polymer of glucose? That's in your muscles. You have a nice little store of glycogen. And then after that glycogen stores runs out, as long as you're receiving a constant blood supply, the blood supply will bring plenty of glucose and you can build your ATP no problem. Okay? What happens next depends on if there's oxygen there or not. So let's first talk about what happens when there's no oxygen. Pyruvic acid, which is right here, has 2 places it can go. It can either enter this cycle right here, if there's oxygen present, and we'll talk about what happens here, or if there's no oxygen present, it has no choice but to be converted into what's called lactic acid. So if there's no oxygen, you form lactic acid. Lactic acid is, as the name implies, bad acid. It starts to build up in muscles and makes you sore. All right? It will eventually get brought out of the muscles, back into the bloodstream, go to the liver, be reconverted back into pyruvic acid, even be made back into glucose, and all kinds of things can happen with it. But in the short term, you're going to be sore. We'll talk about that in a few minutes. But let's say you've got plenty of oxygen. That pyruvic acid now can come over here. So now you have 1, 2, 3 plus 1, 2, 3. You have your pyruvic acid. What's going to happen through a series of events we call the Krebs cycle and what we call oxidative phosphorylation or electron transport. Again, if you don't know this, I'm fine with it. What's going to happen is you're going to end up getting 1, 2, 3, 4, 5, 6. 6 1-carbon molecules. What do we call that? CO2. That's a 1-carbon molecule. So if you take glucose all the way from the very beginning, all the way to the end, using oxygen, you make carbon dioxide, which is why we breathe out carbon dioxide. We need oxygen for that reason, right there, to break down glucose, and we get rid of carbon dioxide for the same reason. We make too much of it, we have to get rid of it. Plants do the opposite, by the way, you didn't know that. Okay? So if we fully break down glucose, we've broken a heck of a lot of bonds there. We've gone from 6 down to single molecules. We've broken a lot of bonds, and we can get an additional, say, 34 ATPs. Okay? So for 1 molecule of glucose, 1 molecule, we can get 2 ATPs over here. But if we have oxygen around, we can get 34 more out of it.